All right, so the plan for today is to continue the discussion that we started yesterday. Sorry, not yesterday, in the last section, which was about we derived we discussed the variational description of Einstein theory. We talked about how we construct generally covariant actions and how we derive energy momentum tensor by varying the generally covariant actions with respect to the metric. There was also a question about what happens if we apply another procedure to a generally covariant action, and the answer is that you will get 0, basically by the definition of the action being generally covariant. What happens is that if one tries to apply another procedure to that action, it will just give 0 identically. So we talked about how to take a matter action and make it generally covariant by coupling it to coupling matter fields to metric. And then we also talked about the pure gravitational part of the action, which was the Einstein-Hilbert action. And then the variation of this full action with respect to metric, which is now a dynamical field, gives us the Einstein equations. So now we want to start from the Einstein equations and talk about conserved energy and momentum. And this will be conserved energy and momentum in asymptotically flat spacetime, as we will see. And then later in this session, we are going to go on and talk about the rotating black hole solutions and the Kerr metric. There's going to be a relatively brief discussion on rotating black holes. I'm not going to dwell too much on that in that subject, but just mention a couple of things about it. Okay, so but now let us first talk about ADM mass, or conserved energy and momentum in asymptotically flat spacetime. So we have the Einstein equation. Now we can derive it in various ways. One thing that we noticed last time was that the T mu nu that we get for matter fields is not good for defining conservation laws in general, because it's not ordinarily conserved, but it is covariantly conserved. And we need something which is ordinarily conserved in order to define, to conserve charges or conserve mass and energy. Okay, but now we want to try to construct such a thing, an object which is ordinarily conserved, and that object is called the pseudo tensor of energy and momentum. So what is the idea? The idea is that let us do the following decomposition of the metric. So let's choose some coordinate system. And in that coordinate system, let's write G mu nu equals eta mu nu plus H mu nu. Notice that this decomposition is not generally covariant. What do I mean by that? What I mean by that is that it means this decomposition is frame dependent. If we go to a different coordinate system, the decompositions in different coordinate systems do not agree with each other. Why? Because so this is not, let me just, this is not covariant, because if I go to a different coordinate system, then the transformation of The transformation of the metric, we know what it is, right? It will be dx mu, dx tilde alpha, dx nu, dx tilde beta, g mu nu. But now if I apply it to this decomposition, if I apply it to eta mu nu, that generically is not equal to eta alpha beta. So this is kind of an arbitrary frame-dependent decomposition, but we will see why it is useful. Soon we will see why this is useful when we are talking about asymptotically flat the space. So let us do this arbitrary decomposition, and then of course we can now plug this expression in here inside Einstein tensor. Remember, Einstein tensor was constructed out of metric and its derivative. So I can plug this decomposition in here and then just expand in terms of h mu nu. So then what I do is that I take the first term in this expansion, I separate the first term in this expansion and call it G1. Sometimes I call it G linear. And then the rest will be G nonlinear. And now, if I just substitute it in the Einstein equations, what we will have is that G1 mu nu, let me also divide by 1 over 8 pi g. This is equal to T mu nu minus 1 over 8 pi g, G nonlinear mu nu. Now this object that we have on the right hand side, this object I call it tau mu nu. And this is called the pseudo tensor of energy and momentum. So why is it called pseudo tensor? Because it's not a real tensor, because it was based on this arbitrary non-covariant decomposition of the metric. So therefore, if I do a coordinate transformation and do again the decomposition in that new coordinates, I will get something that is not related to this by the laws of transformation of tensors. That's why it has got pseudo tensor. But why is it called the pseudo tensor of energy and momentum? Because it is related to energy and momentum. In particular, if you imagine we are in a situation where we are near Minkowski spacetime. So if we can write the metric, so remember metric was expanded like this. If we can write the metric, expand the metric near Minkowski, and these deviations from Minkowski are very small. So therefore near Minkowski, equivalent to saying that this h mu nu is much less than 1, then this pseudo tensor is, then this tau mu nu is approximately the same as T mu nu. So if we are near Minkowski, it is going to agree with what the usual T mu nu gives us. And the usual T mu nu, if we are near Minkowski, it is the energy momentum tensor. So of course, if gravity is weak, then the stress energy tensor for matter gives the right answer, a good approximation for the energy and momentum in that space. The issue is when gravity becomes important, when the curve, when the space-time is not near Minkowski. So it has some connection to energy and momentum, but it has an important property, which is that it is actually ordinarily conserved. And that's the important property of this tensor. Unlike matter T mu nu, this combination is ordinarily conserved. So if I consider d mu G1 mu nu, that is actually identical to 0, where I raise the index by eta mu nu by Minkowski matrix. So this G1 mu nu is still, this object is still linear in H mu nu in the matrix. So this is identically conserved, which implies that also d mu tau mu nu is equal to 0 when the equations of motions are satisfied. So this is a very, very useful property, because once I have a tensor like that, then I can define quantities which satisfy conservation. So therefore, I can use this and define P mu as integral d3x tau 0 mu. Now, of course, at this level, without specifying the asymptotic behavior of the spacetime, this is kind of arbitrary. It's not very useful because, as we said, this tau mu nu is a pseudo tensor. So at this level, it looks like, depending on how we choose this slice, this spatial slice, or in general, what coordinate frame we use to make this decomposition, depending on that, this P is gonna have different values. And of course, that's something that we won't be interested in. So if we want to associate some energy and momentum to a spacetime, it better be unambiguous. It shouldn't depend on our choice of what coordinate system we chose to define tau mu nu. So at this level, this seems rather useless. However, it becomes useful because of the following reason. This linearized Einstein tensor it can actually be written as the total derivative. So this linearized Einstein tensor is something linear in H mu nu, the fluctuations, and this can be written as, okay, so I put this factor -1/2 here, which might sound weird since I'm not defining a new quantity. So this -1/2 that I put here is just because I want to be consistent with my lecture notes, where I define this in terms of something in some other normalization at the linearized level. So apologies for this factor -1/2 here. But okay, so this can be written as -1/2 of the total derivative of somebody else and that somebody else is, now it has a relatively simple expression that, oh, I actually have it here, so I don't need to copy. Okay, so first let me move this down, and here how do I put this here? No. Okay, I managed to move this. Yes. So again, how we define it like this in terms of the linearized G mu nu. And the important thing is that this linearized G mu nu is a total derivative of this new tensor, which is anti-symmetric. Importantly, it is anti-symmetric with respect to these two indices, and it's given by this expression. So I have written in a way that makes it manifestly, shows manifestly that it is anti-symmetric. This anti-symmetry that guarantees the fact that this linearized G mu nu is identically conserved, because there is so here, if you take the d mu of G1 mu nu, it becomes -1/2 d mu d alpha of H alpha mu mu. But ordinary derivatives commute with each other, while this tensor is anti-symmetric with respect to exchange of alpha and mu. Therefore, this object is equal to 0 as an identity. Okay, so now why is it important? Because because now if I defined now we define total for momentum in terms of this integral of tau mu nu, or tau is the zeroth component of tau mu nu, this integral can be reduced to a surface term. So this becomes -1/16 pi g integral. So now here it's important that we have some asymptotically flat spacetime, because it is a total derivative. And now if I have an asymptotically flat spacetime, this integral total derivative, I can reduce it to a boundary integral at large radius. So this integral, as r goes to infinity, the boundary integral of, or let me add some intermediate step in the calculation. So we remember that this tau, we remember that this was a total derivative. So let us plug in the expression. This is -1/16 pi g integral d3x. And here I should put d alpha. So I should plug in this expression, but the index, the upper index here is chosen to be 0. Since it is anti-symmetric, the other index has to be the spatial index. So here we will have di hi0 mu. But now this is a spatial integral of the divergence of something. So I can now reduce it to a surface integral. R going to infinity, the integral over the surface element of HI0 mu. Now, if the space-time if the space-time is asymptotically flat, then this quantity that we define here is well defined, is unambiguous. Why? Because then we can then we can linearize in h mu nu and this p mu that we define is invariant under linear diffeomorphism. So remember, linear diffeomorphisms are these. When in general, when we transform the metric, we wrote what is the general transformation of the metric. If we translate it into a transformation of h mu nu, then the transformation of h mu nu under diffeomorphism will look like the following. It will have d mu x nu minus d nu x mu plus terms that include the order h. So they include xc, but it also include h, or h mu, h alpha beta, the components of h. Now, if we are going to a regime where we can linearize in h mu nu, then we can ignore these corrections. And under these transformations, one can show that this expression is invariant. So as long as we are choosing coordinate systems so that asymptotically h mu nu remains small, then we are guaranteed that we get something well defined. So this object that originally in this form looks coordinate dependent because it is integral of a pseudo tensor. If we are asymptotically flat and we restrict ourselves to this particular set of coordinate system that respect asymptotic flatness, it becomes uniquely defined. And that's why we like this object. So this gives us a good definition of energy and momentum in asymptotically flat spacetimes. And of course, it is conserved because it was made of an ordinarily conserved tensor or pseudo tensor. Okay. Any questions so far?
I have a quick question. So you say that under the diffeomorphism transformation, the p mu is invariant. So did you mean that we will have correction in say xi square, or we don't have any correction at all?
Well, here I want to do uh, I want to do infinitesimal transformations in terms of XC. So if I show that on the infinitesimal transformation something is invariant, that is good enough for my purposes, because what we do is that if something transforms on the infinitesimal transformations, then we can integrate those and find finite transformations. So if it's invariant on the infinitesimal transformations, then it is invariant. You might worry about the additional term here, which is are of order. So what are they? They are actually of order of h times xc. Like for instance, this include something like xc alpha d alpha h mu nu, right? The usual transformation of a function that is defined on the space. So these are the kind of terms that are included in here. Let me show it like this. So these are the kind of terms that are included in here. You might worry about those, but that's exactly the condition that I'm imposing. I'm imposing that these xc's are such that they respect the condition of asymptotic flatness, which means that they have to decay at infinity with the right decay property that I use to define asymptotic flatness. Say, for instance, they have to decay as 1 over r. But then this object will decay even faster. So then I don't need to worry about it. Since I'm taking r to infinity limit here, this argument becomes completely precise. So at any finite r, there will be corrections which are going as higher power, inverse powers of r, but in the limit that r goes to infinity, that becomes a precise statement. Those corrections are exactly 0 in the limit that r goes to infinity. Notice that you will get something non-zero in here, even though r goes to infinity. The reason is that this big H is given as a derivative of the little h. Little h at infinity, as you have seen in the Schwarzschild matrix, goes as 1 over r. And therefore, the derivative of it goes as 1 over r squared as you send r to infinity. But the area of the surfaces or the spheres grows as r squared. So this leading term that you get from here will be finite in the limit. But if you keep any higher order term in here, then they will go to 0. Actually, there are some set of one subset of transformations that do actually change the result. Those are the Lorentz transformations. So those x's that corresponds to Lorentz transformation actually survive, and they just correspond to the fact that when I say asymptotically Minkowski, still I have the choice of choosing a Lorentz frame. So this P mu will be a 4 vector, which can change depending on the choice of that Lorentz frame. So of course, those choices of sigma that corresponds to the different choice of Lorentz frames are allowed when I say asymptotically Minkowski, but anything else should be appropriately decaying at infinity. Other questions?
So if we consider a Lorentz transformation, P mu will be invariant or not?
No, it behaves like a 4 vector. It will transform like a transform with the Lorentz will be multiplied by a Lorentz matrix.
But can we consider Lorentz transformation as a diffeomorphism transformation?
Yes, it's a particular choice of. So what is a diffeomorphism? You change your coordinates from one. You go from one set of coordinates to another set of coordinates. A particular subset of that are the Lorentz transforms. That's a particular subset for which this equality actually holds.
Yes, but my question is, as we saw that the P mu is invariant under any diffeomorphism transformation, right?
Well, actually, it's not invariant on the Lorentz transformation. So this, okay, so yes, so to be more precise, so let's say you want to do a Lorentz transformation. Well, how does it look? An infinitesimal Lorentz transformation is like, so for instance, t goes to t minus some small parameter times x. X goes to x minus some small parameter times t. So if I want to identify the xc, the parameter of transformation in the case of Lorentz, that xc would be something that is linear in the coordinates, right? So this is something that normally I wouldn't allow myself to do if I want to preserve asymptotic flatness, except in the case of Lorentz. So if I do Lorentz transformation, then I'm allowed to do that. I'm allowed to pick these xc's to be growing like linearly with the coordinate. That is the only case in which you can keep these terms, and then you will change the answer. So to be more precise, any diffeomorphism except the Lorentz transformation, for any diffeomorphism except Lorentz transformations, I ignore these terms. And then this part will vanish if you plug it in here. So this expression is invariant on the this part. If you do Lorentz transformation, which are compatible with the assumption of asymptotic flatness, then you have to keep these terms because xi are actually growing at infinity. So I keep these terms and plug it in here, and I will get a Lorentz transformation of the result.
So we can conclude that P mu under this diffeomorphism transformation, P mu transform as P mu plus xi square, something like that.
No, it's not psi squared. It's always linear in xc.
No, I mean P mu. I mean the change in P mu. Of the order xi squared.
But see, I'm doing an infinitesimal transformation. infinitesimal coordinate transformation. So which means that I only keep to linear order in XC.
No, I mean, I was just saying, if we keep the higher order terms, I will get the lowest order term that will contribute to the change of P mu will be of size square.
Well, the psi square terms I would get by integrating the linearized transformation. So if I establish that the linearized transformations leave P invariant, then it is invariant even when I integrate those. Again, as long as I am satisfying the assumption of asymptotic flatness. Now, one way to get not to be worried about Lorentz transformation is I fix a Lorentz frame at infinity. That like I have a set of observers at infinity who define for me a Lorentz frame. That already kills the possibility of this size growing linearly at infinity. So I wouldn't care about this term. And then for these linearized diffeomorphisms, I know that this is invariant. So then in with the choice of Lorentz frame, I get one unique answer for P mu.
But I have another confusion. So as long as we have a non-zero value for P mu, then it breaks the Lorentz symmetry, right?
Uh-huh.
Right.
Yes, yes.
We have some particular kind of configuration of matter, which is giving me a particular direction.
Mm-hmm. Yes.
And we're breaking the Lorentz symmetry.
Yes.
Okay. Okay.
Yeah, so this is, we are associating a total energy momentum vector to the whole space-time. This breaks Lorentz symmetry. You have a preferred frame, which is the rest frame of the whole space-time. And in that rest frame, then the energy, the momentum will be zero, and the energy is called the ADM mass of the space-time. Other questions? Okay, so now we can also define in a similar fashion. We can also define angular momentum or a spin. So we can talk about total angular momentum of the space-time, and that is defined in a very natural way in terms of this same pseudo tensor. At 0k. So again, you can see that if gravity was weak, then this tau would coincide with the matter energy momentum tensor, and this is clearly the natural definition of the angular moment. But this object has the property that, again, it is useful, is well defined in asymptotically flat spacetimes, because, again, one can show that this reduces to a surface term, and that surface term is invariant under linearized diffeomorphisms. Okay, I don't want to talk too much about this angular momentum, but I mention it because then it will be a natural connection to the next topic, which is a rotating black hole. Because the statement is that the total angular momentum of the spacetime is also a well-defined quantity if we are asymptotically flat. And of course, if I ask what is the total angular momentum for Schwarzschild, so Ji for in Schwarzschild geometry is obviously 0 because of the spherical symmetry. So now you could ask, what happens if I drop something which has angular momentum inside the Schwarzschild black hole? Or what happens if a rotating star collapses into a black hole? Then we would expect that the resulting spacetime will have non-zero angular momentum. And it is actually shown that the final result of that collapse, or the this black hole solutions which have non-zero angular momentum, are unique. Basically, they form a two-parameter family of solutions of vacuum Einstein equations, which is described by the Kerr metric. So here is the Kerr metric, which is a bit scary, so I have written it. Before, because it takes a lot of time to write it. So, so it is much more complicated than the Schwarzschild metric. So let us just go over some of the properties of the Kerr metric. It has, again, the coordinates that are used here are the same coordinates. At least they have the same names, maybe not exactly the same meaning of the coordinates used in the for the Schwarzschild spacetime. This A is a fixed parameter which characterizes the angular momentum or the angular velocity of this black hole. So the angular velocity would be related to this A parameter. This delta and sigma are these functions given here. So one thing that you can immediately notice is that if you take the limit of A going to 0, if you set A to 0 in this metric, then you will recover the Schwarzschild solution. What other thing we can notice here? So the other thing to notice is the symmetries of this spacetime. So as you can see here, of course, we don't have the spherical symmetry anymore because now we have a rotating object. So the spherical symmetry is lost, but axial symmetry is still there, right? If I have a rotating object, then I can have rotations around the axis of rotation. So that corresponds to the shifts of this phi variable. So as you can see, this metric makes it obvious. There is no explicit dependence on this phi coordinate in this metric. Moreover, there is no explicit time dependence in this metric. So this metric clearly has two symmetries. It has axial symmetry and it has a time translation symmetry. Or in other words, it is stationary, which means that it has time translation symmetry, or a more fancy way of saying it is that it has a time like killing vector at infinity xc, which is dt, and then it is axially symmetric or axisymmetric. So it has another isometry vector psi, or it's called psi, which is d phi. Let me just mention this. So I don't know if Paolo talked about isometries or isometry vectors. So this is just so we casually talk about the symmetries of the space-time. Of course, we can make it a bit more formal. What does it mean to have a symmetry of a space-time? There is some transformation that doesn't change the metric. Now, we saw that on the infinitesimal transformation, the change of the metric is minus del mu xi nu, then nu xi mu. So we say we have an isometry if we have a choice of xc for which this is equal to 0. So now I call this dt xc, but this is this xc is a different xc, so maybe I can give it a different name. Let me give this a different name here. Let me call this chi. So the statement is that if we compute these quantities for linearized diffeomorphisms that are generated by this vector, and this is the vector field, defines a vector at every point in the spacetime, or consider diffeomorphisms that are generated by this vector field, the metric will not change. This is kind of obvious because this vector field is just a change in time variable, in time t coordinate. And the way I have written the metric, it makes it completely obvious that this is a symmetry of a space. The metric has no t dependence. And then similarly for phi. It's not always possible to make isometries manifest at the level of the metric. For instance, we had the Schwarzschild metric before. If you remember, the Schwarzschild metric was also t independent and phi independent. But the isometries of Schwarzschild metric was bigger than the isometries of the Kerr metric. So even though it had the dependence on theta, for instance, it had full spherical symmetry. So it's not always possible to make the symmetries of the metric manifest by a choice of coordinate system. Anyway, here is the case. There are these two isometries, and it is manifest at the level of the metric. Just a moment, let me close the window. Okay, so one thing that we have seen, let me see. So let me just give it its name. This is called isometry. And then the one important point from isometry is the fact that they give us conservation laws, right? This you have already seen also. So again, that we have seen it perhaps in a less formal way. Like for instance, we saw that if the metric does not depend on a coordinate, then we have a conserved quantity. So the more a more abstract version of saying that is that if I have an isometry, then we will have a conservation law for geodesics, which is xi mu p mu equals constant. On geodesics. So this is something that you can verify using just the definition of isometry. Now, in particular, if I say, for instance, say xi mu is just the generator of time translations. So xi mu is just dt. So it is 1, 0, 0, 0. Then this xi mu, well, maybe I use the other name, so we called it chi. Then chi mu, p mu is nothing but p0 or pt, which you saw is a conserved quantity along geodesics. Similarly, if I have axial symmetry, then we have conservation of angular momentum along geodesics, which you can again express it in this form. Then P5 would be, for instance, conserved. Okay, so this is, I guess, enough for isometries. I want to discuss some properties of this this Kerr metric. Any questions?
Sorry, Professor.
Yes.
Oh, please. Do you say this Kerr metric describes a rotating black hole?
This metric, yes, it describes rotating black holes. Yes.
Okay. Like, so when you say a rotating black hole, what do you mean by rotating?
Oh, what I mean is that if you take this metric, which is asymptotically flat, so that is something that you can verify. If you send r to infinity, so one other property of this metric is that this is property 1, property 2. Limit r goes to infinity of Kerr equals Minkowski. So it is asymptotically flat. If we take this Kerr metric, which is asymptotically flat, and compute the angular momentum using this general formula for the metric, we will get something non-zero. Does it answer your question?
Actually, I have this misconception. I was just thinking wild. I was thinking like the word rotating black hole means like I mean, there is a kind of rotation or something, I don't know. That's why I want to confirm what is meant by the word rotating in that instance.
Can you ask it again?
I said I have this wide idea of like when you said rotating black hole, I thought probably there's a kind of rotation or something going on in there. So I wanted to ask if that idea was actually right, that when you were mentioning the kind of symmetries that the metric has, why doesn't it have why doesn't it have a rotational symmetry? So that was why I asked you what was meant by the word rotating in the name of the black hole.
But what I understand is that you are asking what is rotating in there. Is it true?
Yeah, something like that. Yeah.
Like in the case of a rotating star, you imagine something is rotating there, some matter fields that are going around. Are you asking what is rotating in the case of a black hole, rotating black hole?
Yes, exactly. What is a rotate? What makes it a rotating black hole?
Well, I don't think I can give a very good answer to that. I'm gonna say some things that might make it a little bit more intuitive, but I cannot point to something that is actually rotating in here. It's the result of it's a space-time, it's a vacuum solution. Exactly because it's a vacuum solution, I cannot point to something that is rotating because it's a vacuum solution. But it will have some properties that might make it a bit more intuitive, but I would say the best quantity that identifies rotation is the total angular momentum of the spacetime, which is non-zero for this metric. You could have some more maybe some more abstract questions about what's the meaning of a rotation in vacuum. That is actually related to some old idea of Mach. There is something called Mach principle that in fact was motivating for Einstein for the constructing the general relativity. And indeed, general relativity is not Machian in the sense that there is a rotating black hole solution, while Mach principle wouldn't actually. If it was really Machian, this wouldn't make much sense. But I cannot say much about it here. But okay, let me talk about some properties of this metric, and it might make it a little bit more intuitive why it is rotating. Other questions? Okay, you could ask why do I call it a black hole in the first place? So maybe one indication is that if I send A to 0, it becomes Schwarzschild. But still, I haven't really said why I call it a black hole. Also, I'm not going to derive it. It's much more complicated to derive this metric compared to Schwarzschild, and it took much longer to find this solution compared to the Schwarzschild. So let's understand why we call it a black hole. So it has a horizon. That's why we call it a black hole. So it has a coordinate singularity, first of all. This has a coordinate singularity at when this delta goes to 0. So there is a point, so there is a coordinate singularity. And that coordinate singularity is not, this is not similar to the case of the Schwarzschild. Remember that in the Schwarzschild geometry, GRR would diverge at R equals RG at the gravitational radius. So here is a similar thing. There are two radii at which GRR diverges, and that is actually, now we will see that is actually a horizon. So how do we see? There is this, if you look at the RR component of the metric, is given by sigma divided by delta. So delta has this expression. So if I look for the zeros of delta, that corresponds to the poles of GRR. So delta equal to 0. That has two solutions. R plus minus equals GM plus minus the square root of G squared M squared minus A squared. Now from here, we will also see that so these solutions then become complex, and beyond that, there will be an actual physical singularity at the point that now I'm gonna call it the horizon. So actually A has to be less than or equal GM. So we have this R plus and R minus, the points at which, so at these points, GRR is equal to infinite. So we have a coordinate singularity. At least a coordinate singularity. Maybe it could be a real singularity, but it turns out that it is not a real singularity. It is just a coordinate singularity, just like in the case of Schwarzschild. So one can actually see that infalling observers or nullers can go through that point, R equals R plus, without anything dramatic happening to them. There is no curvature blowing up, as long as we satisfy this condition. Now, why do I call it the horizon? Let us consider the form of this metric. Go near R equals R plus. So R plus is the bigger solution of this equation, and consider a time like geodesics. So let us study the property of R equals R plus hypersurface. So the claim is that this R equals R plus hypersurface is null. So it's a null hypersurface at a fixed R, and that is what the horizon does. So remember, horizon was the boundary between a region where you could send signal to infinity and a region where you couldn't send it. So now we have identified the hypersurface at R equals R plus, and now I'm going to show that this is a null hypersurface. So it becomes a boundary between the region when you can send out signal to infinity and the region where you cannot send it. That's why I call it a horizon. So why is it null? Because let us consider some vector, we want to consider a causal curve, which is described by a 4 velocity u mu. which I wanted to live in this R equals R plus surface. Therefore, it will not have any UR component. It has a UT component and a U phi component. I set U theta to 0 too. You can see that if you set it, if you keep it non-zero, it only makes, doesn't change my conclusion. So let us consider this metric and consider a causal curve in this metric with the tangent given by this u mu. So we want to ask or see if there is such a causal curve. So what does it mean to that we have a causal curve with this for velocity? It means that if I look at g mu nu, u mu u nu, for it to be a causal curve, this quantity has to be less than or equal to 0. So if it is massive, it has to be less than 0. If it is null, then it will be 0. So if you plug it in that metric, or use that metric to evaluate this quantity, what you will get is this. You will add, so then you call it causal. So at R equals R plus, what we get is that this g mu nu u mu u nu is equal to sine squared of theta divided by sigma times a ut minus r plus squared plus a squared times u phi squared. So what happens is that, and this sigma, let me just remind you, sigma at r equals r plus is a positive definite quantity. So this is just a positive overall factor. And what we see is that this quantity, this normalization of the 4 vector is actually positive or non-negative. It can be 0, but it cannot be positive. So that's why this hypersurface is a null hypersurface. I cannot have any time-like curve in this hypersurface. I can only have null or the space-like curves in it. The null curves that live in here, they will. So these are analogous to the null curves that we have in the horizon of a Schwarzschild black hole. Those are called the generators, the null generators of the horizon. So the fact that this is positive definite, sorry, non-negative, it implies that this state, that this hypersurface is null. And therefore it is a horizon. Well, one has to also see the fact that things can go through it, so it's not really singular. But at least this is an indication that it is the horizon. Now, this metric or this space-time has another. One thing that you can see here already, which is kind of useful, is that if this null generator, so if I set this to 0, I will get some null curves. Now here you can see some property of this null generator. These null generators are actually rotating. So that is something that allows us to define something which is usually called the angular velocity of the black hole, or the angular velocity of the horizon is defined by finding the angular velocity as would be defined by the asymptotic observer for these null generators of the horizon. So it is u phi divided by ut. So u phi, remember, the u phi is d phi by d lambda, where lambda is our affine parameter, and ut is dt by d lambda. So u phi by ut is d phi by dt. So this is the proper way to define angular momentum, angular velocity in the coordinates of asymptotic observers, and this ratio is equal to a divided by r plus squared plus a squared. So again, the angular velocity is linearly proportional to a. So this a parameter is really parameterizing the angular velocity of this black hole. What else? So that, yeah, so this metric has another interesting property, which is the fact that it has an ergosphere. So what is the ergosphere? So we find that there is a coordinate singularity. So let's look back at this metric. There's a coordinate singularity when this GRR component diverges. Before getting to that point, to that coordinate singularity, there is a bigger region in which the coefficient of the TT component of the metric changes sign. So, and that region is important because of what we will see now. But so let us see when this GTT component changes sign, or in particular when GTT becomes 0. So the boundary of that region. And so ergosphere when GTT becomes larger than 0. So if I set GTT equal to 0, then it gives me the following equation. R of ergosphere is a function of theta, and this is equal to GM plus the square root of G squared M squared minus A squared cosine squared of theta. So the radius of ergosphere when GTT becomes 0, it depends on theta. Now you can also compare it with this R plus. If you compare it with R plus, you see that at theta equals 0 and pi, they coincide, but for different thetas, the ergosphere is at the larger radius compared to R plus. So if I want to draw if I want to draw a picture of the side view of the Kerr black hole, there will be the sphere that is the horizon, and then there will be the ergosphere. Well, this wasn't very artistic, but you get the idea. So if the black hole is rotating along the z direction, in this direction, so you have omega h here, then well, there will be there's this region, which is the ergosphere. Now, what happens in the ergosphere? So in the ergosphere, GTT is larger than 0. So let us again look at the metric. What does it mean that GTT is larger than, or maybe we don't even need to look at the metric. What happens is that GTT in the ergosphere is larger than 0, but the only other component of the metric which has indefinite sign, or it can let's again go back to the normalization of the for velocity of the causal curves, right? So we know that the causal curves should normalize to some non-positive quantity. In particular, time-like curves should be, the for velocity of time-like curve should be the square to -1. Now, normally in Minkowski spacetime, the reason you get a negative value is that the TT component of the metric is negative. Remember, I'm using a mostly plus signature, so the TT component is negative in my notation. So normally in Minkowski spacetime, this arises from the fact that the T component of the metric is negative, and every time-like object, any observer or any signal that has a non-zero UT component. Now here, when GTT becomes negative, so when GTT becomes negative, then in order to have non-positive normalization, then what we need is that we have to have non-zero phi dot, because if you look at if you look at for a generic, so if we look at G mu nu U mu nu, then this is equal to GTT UT squared plus GRR UR squared. Now I'm looking at the generic for vector, for velocity. G theta theta U theta squared plus G phi phi U phi squared plus twice GT phi UT U phi. Now, all of these terms are positive or non-negative. So these are all non-negative. So in order for this full normalization to be non-zero, we need to have, so for causal curve, we need to have U phi non-zero and actually positive for my choice of sign of A. So if I take A to be positive, then we need to have U phi larger than 0 for time-like curves, or for all causal curves. So why? Because, so let us go back to the metric. So here you see that this GTT has become positive. This component is positive, this is positive, and this is positive. The only non-positive component of the metric is GT phi, So if we want the line element for the causal curves to be non-positive, to be negative for timeline curves, so 0 for causal curve, we need to have non-zero change in phi, or non-zero phi dot in the right direction. So phi dot has to be positive. What does it mean? It means that everything should co-rotate with the black hole in the ergosphere. So the light cone inside the ergosphere is tilted so that nothing can have 0 phi dot. Everything should have non-zero velocity in the phi direction. So all observers, signals, etc. Everything that is described by causal curves have to co-rotate inside ergosphere.
Professor, sorry, one question.
Yeah? Yes.
When you put GTT equals to 0, you find two solutions for the radius, no? One with the ergo radius of the ergosphere with a plus, and the other with the minus the square root, no?
Let's see. Yes, this is a quadratic equation for R. Yes, I'll find two solutions. Yeah.
My question is, what does it represent another solution with a minus the square root?
Well, that other solution will be in the interior of the horizon. So that is yeah, one has to be a little bit careful, because inside the horizon, once you go inside once you go at r less than r plus, then the r coordinate changes sign too. So then GRR will be negative inside. Like similar to the Schwarzschild case. R becomes a time-like coordinate as you go inside. Now then there will be and the inner horizon. So here we had R plus and R minus, and I focused on R plus, which is called the outer horizon. There is also an inner horizon when this GRR again becomes infinity. Yes. So there is inner horizon, and then this other solution for the ergosphere will be even beyond that, or at a smaller r compared to that. Well, the physical interpretation of that is not totally clear, because it is generally believed that the inner horizon becomes singular in a physical setup. So what happens after the inner horizon, it might not necessarily be, or what you infer from this metric, but this is a metric which is very symmetric. The idea is that if you perturb this metric, then the behavior near the inner horizon might dramatically change. And then it might not be very relevant what you get from this metric beyond that inner horizon. Plus the fact that whatever happens there is the screen from the asymptotic observer. So this rotating black holes actually exist in our universe. We see them, and the main phenomenology would be coming. Their phenomenology would depend on what happens outside the horizon, not inside the horizon, because we don't see anything that is inside the horizon. At least classically, we don't see it, and quantum mechanically, we might well, still there is a puzzle of how we can probe the interior of the black hole, even at the theoretical level. But at the observational level, for sure, we don't see anything from the black hole interior beyond the horizon.
One question, Professor. So can we conclude that inside the ergosphere, the metric signature is changed? I mean, it's not the Minkowski signature.
No, you cannot conclude. You still have local inertial observers there for whom the metric is Minkowski. Oh. Okay, anyway, I didn't want to continue. Yes, you'll have local inertial observers whose metric is Minkowski. So the causal structure is still there. And as long as you have the causal structure, you can talk about local inertial first. It's just that the coordinates that you use can change their identity. In fact, it doesn't mean that this coordinate system is a bad coordinate system. It covers the ergosphere. It's just that the GTT is zero. That really, the only meaning of that is that this time-like isometry that we had in this space-time, once you go inside the ergosphere, that time-like isometry, it becomes a space-like. And that has interesting consequence that I wanted to mention, but now I just say it in words. There is something called the Penrose process. So we know that there is a conserved energy. We just mentioned it. There is a conserved energy when you have a time-like isometry, that is PT, for instance, with lower index. Now, since this time-like isometry inside the ergosphere becomes a space-like, then what it implies is that you can have processes in which a particle from infinity is dropped inside the ergosphere. It decays into two particles. One of those two particles goes inside the black hole with some negative energy, and something comes out with a bigger energy. And this is called the Penrose process. And this is allowed exactly because this time-like isometry becomes a space-like. So inside the ergosphere, it's not, you don't have to have positive P0 or negative P0 for every part. Other questions?
Just one question following the previous one. Uh, in between the two, the inner and the outer horizons, can we have stable orbits? Is there a possibility to have them, or?
Between inner and outer horizons? No, because in between inner and outer horizons, R becomes a time-like variable. So if you remember, or what we mean by orbits? The orbits, we mean the things that go at fixed R or have some fixed range of R's, but that is only possible if R is a space-like coordinate. When it becomes a time-like coordinate, then it has to run in one direction. Sorry, yes?